Hello friends, this is our fourth episode in our series on vectors. The last time we defined one way of multiplying two vectors known as the dot product. Recollect that we had defined A dot B as the magnitude of A into the magnitude of B into cos of the angle between them, that is theta. Theta is incidentally the smaller angle between A and B. Observe that A dot B was a scalar. A dot B was 0 if and only if A was perpendicular to B, was a condition for non-zero vectors A and B. And then we had A dot B in terms of the components of A and B, that is A1, A2, A3, B1, B2, B3. A dot B is equal to A1, B1 plus A2, B2 plus A3, B3. In this episode, we shall define another way of multiplying two vectors known as the cross product or vector product, because this product gives us a vector. Here is our definition. If A and B are two vectors and the smaller angle between them is theta, then A cross B is defined as the magnitude of A into the magnitude of B into sine of the angle between them into the unit vector n, which is perpendicular to both A and B, in such a way that A, B and n form a right-handed triad. What does that mean? That means that if I take my thumb, forefinger and middle finger of the right hand, put my thumb along A, my forefinger along B and hold my middle finger at right angles to A and B, then the unit vector n lies along the middle finger. This is also the way in which a right-handed screw would move when rotated from A to B. Note that A cross B is a vector which is perpendicular to both A and B. The magnitude of A cross B is magnitude of A into magnitude of B into sine theta. Note that sine theta will be positive because the smaller angle theta between A and B will lie between 0 and 180 degrees. And the unit vector can be written in terms of A cross B as the vector A cross B divided by the magnitude of A cross B. We have some more observations for you here. A cross B is equal to minus of B cross A, because in B cross A the direction of the vector n will be reversed. 2. You can see that A cross B will be 0 if either A is 0 or B is 0 or sine theta is 0, that is theta is 0 or 180 degrees, which means that A is parallel to B. Parallel means either in the same direction or in opposite directions. So this becomes a condition for parallelism of two vectors. In particular, A cross A is 0. As a corollary, we can observe that if I, j, k are the basic unit vectors, then I cross I, j cross j and k cross k are 0. Also note that from the very definition of A cross B, I cross j is equal to k, j cross k is equal to I, k cross I is equal to j. Why is this? Because our x, y and z axes also form a right-handed triad. The magnitude of I and j are both 1 and the angle between I and j is 90 degrees. We now explore the connection between cross product and the earlier operations that we had defined, namely scalar multiplication, vector addition and dot product. First, let us look at the connection between cross product and scalar multiplication. We would like to know if this result is true, lambda A cross B is equal to A cross lambda B is equal to lambda of A cross B. And I think you will find it extremely simple to verify that this is indeed true. And before we explore the connection between cross product and vector addition, let us make a connection between cross product and dot product. Recollect that dot product is defined in terms of cos of theta and cross product in terms of sine of theta. We do know that cos squared theta plus sine squared theta is equal to 1. So, why not try to square A dot B as well as A cross B and add the two. A dot B squared plus A cross B squared, does it give us A squared into B squared? Let us see. After squaring and simplifying, we get A dot B squared is A squared B squared cos squared theta, and A cross B squared, which is the magnitude of A cross B squared, is A squared B squared sine squared theta. Take A squared B squared common and you get your result. And now we come to the connection between cross product and vector addition. What we would like to know is cross product distributive over vector addition, just like dot product was distributive over vector addition. Let us put this in the form of a theorem. A cross B plus C is equal to A cross B plus A cross C. We would like to be able to prove this result. Now, what we do is we first take the simple case in which A is perpendicular to both B and C. Why do we do that? Because we notice that if A is perpendicular to B, then A cross B will merely be the magnitude of A into the magnitude of B into the unit vector perpendicular to both. And similarly, A cross C would be having magnitude equal to magnitude of A into magnitude of C. And if A is perpendicular to both B and C, then it will also be perpendicular to B plus C. So, even in this case, the magnitude of A cross B plus C would merely be the product of the magnitudes of A and the vector B plus C. So, let us first consider this case, case 1, in which A is perpendicular to both B as well as C. Now, look at my diagram very carefully. Suppose I draw my vector B equal to OB and my vector C equal to OC, and I draw, using the parallelogram law of addition, the vector B plus C, which I call OD. Let the angle between the vectors B and C be theta. Now, here is my vector A, which is assumed to be perpendicular to both B and C, and hence to the plane containing B and C. That plane I call P. Now, let us look at the vectors A cross B, A cross C and A cross B plus C. Note that A cross B has to be perpendicular to A, so does A cross C and A cross B plus C. Hence, all these three vectors must lie in the plane perpendicular to A, namely the plane P. Secondly, A cross B must also be perpendicular to B, A cross C to C and A cross B plus C to the vector B plus C. So, keeping that in mind, let us draw the vectors A cross B, A cross C, A cross B plus C as the vectors OP, OQ and OR in the same plane P. Note once again that OP has to be perpendicular to OB, OQ has to be perpendicular to OC and OR has to be perpendicular to OD. From very simple geometry, it can be seen that because angle BOC is theta, therefore, angle POQ must also be theta. And now, let us look at the lengths OP, OQ and OR. OP is the magnitude of A cross B, which would be A into B into sine of the angle between A and B, that is AB, which is A into OB. Similarly, OQ is the magnitude of A cross C, which turns out to be A into OC. and OR is equal to A into the magnitude of B plus C, which is nothing but A into OD. So, we find that the lines OP, OQ, OR are proportional to the lines OB, OC and OD. Thus, let's look at the diagram again. OPRQ must also form a parallelogram just like OBDC. In other words, OR vector must be the resultant of the vectors OP and OQ. However, OR was nothing but the vector A cross B plus C, and OP and OQ were A cross B and A cross C respectively. Therefore, what we have proved is, in this case, A cross B plus C is equal to A cross B plus A cross C. But this was only one case. So, let us try the second case. Case 2, general case. Now, what I try to do is to write A cross B as A cross B2, where B2 is a vector which is perpendicular to A. Okay. So, let me show you how we do this. B, of course, now need not be perpendicular to A. However, what we do is, I will show you on a larger diagram. This is my vector A and this is my vector B in general, and the angle between them let us call theta. Now, if I think of my vector A as being along the x-axis and the vector and the y-axis to be in the plane containing A and B, and then you have your z-axis. Then I can write the components of the vector B along x-axis, y-axis and z-axis as B1, B2 and naturally 0. In other words, I can write vector B as the vector B1 plus the vector B2, where B1 is parallel to A and B2 is perpendicular to A. Clearly, B1, that is the magnitude of the vector B1, will be B cos theta, and B2, which is the component of B in the perpendicular direction, will be B sin theta. Right? Now, how do these help us? Let us look at A cross B. A cross B, by definition, is mod A into mod B into sine of the angle theta into the unit vector n perpendicular to both A and B. Here is a smaller version of the diagram I had earlier drawn. Now, we can see that B sin theta is nothing but B2. So, what we get is A cross B is equal to A, that is mod of A into B2 into the unit vector n. And this is nothing but A cross B2, because the unit vector n is perpendicular to both A and B and hence to the vectors A and B2 as well. So, this is nothing but A cross B2. The angle between them, you can see, is 90 degrees. Similarly, I can express A cross C as A cross C2, where once again I have split up the vector C into C1 and C2, where C1 is parallel to A and C2 is perpendicular to A in the plane containing A and C. Finally, since B plus C can also be split up into two vectors B1 plus C1 and B2 plus C2 lying along A and perpendicular to A respectively, I can once again write A cross B plus C is equal to A cross B2 plus C2. Now, what have we achieved? Well, by the earlier case, A cross B2 plus C2 will be equal to A cross B2 plus A cross C2, because A is perpendicular to B2 and C2. But these by 1, 2 and 3 imply that A cross B plus C is equal to A cross B plus A cross C. So, by making use of case 1, I can prove the general case. So, we have proved that cross product is distributive over plus. And this gives us an extremely important rule for A cross B in terms of the components of the vectors A and B. Suppose A is A1i plus A2j plus A3k and B is B1i plus B2j plus B3k, then we can prove that A cross B is given by this determinant. This means A2b3 minus A3b2 into I minus A1b3 minus A3b1 into j plus A1b2 minus A2b1 into k. Right, the usual rule for determinants. And this can be proved very easily by writing A and B as A1i plus A2j etc. and using the distributive law. And of course, the fact that I cross I is 0, j cross j, k cross k are 0 and I cross j is k etc. And now, a couple of simple geometrical interpretations of A cross B. The first, modulus of A cross B represents the area of the parallelogram with adjacent sides given by the vectors A and B. Let us have a look at it. This is the vector A, this is the vector B, and if this angle is theta, then the height of the parallelogram is given by the magnitude of B sin theta, right. Sin theta is opposite side over the hypotenuse. So, the area of the parallelogram, which we know is given by base into height, is equal to the magnitude of A into H, which is A into B sin theta, which we know is the magnitude of A cross B. And the second geometrical interpretation, the area of a triangle with sides A, B and C is given by half magnitude of A cross B, which is the same as half magnitude of B cross C, or half magnitude of C cross A. Let us look at any one of these. Suppose my triangle is A, B, C, where the sides opposite to the vertices A, B and C I will call vector A, vector B and vector C. Let theta be the angle between this vector and this line. Often theta is known as the angle B, right? I am referring to it as theta. Now, we know that the area of the triangle is given by half base into height, and after that it is as simple as the earlier one to prove that this is half C cross A. Do that yourself, and I would like you to prove as a corollary an extremely important formula which we call the sine formula, and that is, if you call the angles enclosed by these sides A, B and C respectively, then it can be proved from this result that sin A by the length of the opposite side A is equal to sin B by B is equal to sin C by C. Remember that when you are using the formula for cross product, then the angle between the two vectors, for instance between A and C, will be this angle, which is pi minus C. But sine of pi minus C is nothing but sine of C, and so this formula will follow very easily. And here are some simple problems for you to solve. First, suppose you are given 3 vectors A, B and C in terms of their components along I, J and K. Calculate A cross B dot C and A cross B cross C. Let us look at the first. For this, we will have to make use of the component rule for A cross B. That is, A cross B is given by this determinant in which the first row is I, J, K and the second row are the components of A, namely 2, minus 3 and 1. The third row are the components of B, namely 3, 0, 4. We are not concerned with C in this problem. Now, let us calculate this. The first will be I into minus 3 into 4 is minus 12, 1 into 0 is 0, then I have minus J into 2 into 4 is 8, minus 1 into 3 is 3, lastly plus K, 2 into 0 is 0, minus 3 into minus 3 is minus 9, and so we end up with minus 12I. I can write my lambda before or after, but usually it is written before the vector. So, I can write this as minus 12I, and this was 5. So, I have minus 5j, and this is 9. So, this is plus 9k. This is my answer for A cross B. And then in the second part, when you take A cross B dot C, then all I have to do is to use the component rule for A cross B, or rather for the dot product of 2 vectors. So, if we go back and look at our C, that was given to me as I minus 2j plus 3k, then the dot product of these 2 vectors is given by the point-wise product of their components, coordinate-wise product of their components. So, that is equal to minus 12 into 1 plus minus 5 into minus 2 plus 9 into 3, and this you can simplify. This will turn out to be a scalar. Similarly, A cross B cross C will be obtained by taking the cross product of this vector A cross B with the vector C, once again using the determinant for the component rule of cross product. Another problem: find a unit vector perpendicular to the plane of A and B. Now, we know that A cross B is a vector perpendicular to the plane of A and B. So, the unit vector n will be given by the vector A cross B, which you will calculate as you have just done, divided by the magnitude of A cross B. Now, if A cross B, A and B are the vectors that were given to me earlier, and we have got A cross B, do you remember what the magnitude of A cross B will be? It will be the square root of, that is the positive square root of, the sum of the squares of the components, that is the positive square root of (144 plus 25 plus 81). And I think you can calculate that yourself. You just have to divide the vector A cross B by that scalar, and that will give you the unit vector perpendicular to the plane of A and B. Our second problem is similar to the first. Find a vector of length 5 perpendicular to the plane of A and B. All we need to do is to multiply the answer in 2 by 5. So, this vector will be 5 times A cross B divided by modulus of A cross B. Here is a problem in which we are given the magnitude of A, the magnitude of B and the magnitude of A cross B. We have to find the magnitude of A dot B. So, what is it that we should do? Recollect that we have proved a relationship between A cross B and A dot B. That is, A dot B squared plus A cross B squared is equal to A squared B squared. In this problem, we are given A, that is magnitude of A, magnitude of B, and also magnitude of A cross B. So, we can square and substitute in this to get square of A dot B. Then taking the square root of A dot B squared, we will get the magnitude of A dot B. Another problem, you have some identities given like this, which you have to prove. A cross B plus C plus B cross C plus A plus C cross A plus B is equal to 0. Now, although it looks difficult, but it is extremely simple, because all you have to do is to use your distributive law to open this out, and then use the fact that A cross B is minus of B cross A to cancel out the terms in pairs. Another problem, which is somewhat similar. You are given something, that is A cross B is C cross D, and A cross C is equal to B cross D. Show that A minus D is parallel to B minus C. All that you have to do is to take the cross product of these two vectors, use your distributive law to open it out, and then use these above given facts to show that the cross product of these two is 0. Finally, we have a problem. A cross B whole squared is equal to this determinant A dot A dot B, B dot A and B dot B. Once again, all you have to do is to make use of the relationship between A cross B and A dot B, and you will immediately be able to see that this is what you get, because when you simplify this determinant, you get A squared into B squared minus A dot B squared, since B dot A is equal to A dot B. Well, that's all for today. Thank you.